Hello! Thank you for watching, and welcome to the next video in my series on basic statistics. Now, as usual, a few things before we get started. Number one, if you're watching this video because you are struggling in a class right now, I want you to stay positive and keep your head up. If you're watching this, it means you've accomplished quite a bit already. You're very smart and talented, and you may have just hit a temporary rough patch. Now, I know with the right amount of hard work, practice, and patience, you can get through it. I have faith in you. Many other people around you have faith in you. So should you. Number two, please feel free to follow me here on YouTube, on Twitter, on Google+, or on LinkedIn. That way, when I upload a new video, you know about it. And it's always nice to connect with my viewers online. Life is much too short and the world is much too large for us not to take the opportunity to connect when we can. Number three, if you liked the video, please give it a thumbs up. Share it with classmates or colleagues or put it on a playlist. That does encourage me to keep making them for you. On the flip side, if you think there is something I can do better, please leave a constructive comment below the video, and I will try to take those ideas into account when I make new ones for you. And finally, just keep in mind that these videos are meant for individuals who are relatively new to stats. So I'm just going over basic concepts, and I will be doing so in a slow, deliberate manner. Not only do I want you to know what's going on, but also why and how to apply it. So, all that being said, let's go ahead and get started. So this is our next video in our series on hypothesis testing. Now, up to this point, we've talked a great deal about what type 1 error is and what type 2 error is, and we used curves to actually illustrate what they are visually. And remember that type 1 error is easy to control because we choose it. So we choose an alpha level of 0.05 or 0.10 or 0.01, whatever you would choose it to be. And remember, that is the comfort level we have with making a type 1 error. So remember, a type 1 error is when we reject the null hypothesis incorrectly. So in our population, we may get a sample mean that's way beyond what we would expect it to be. However, it does belong to that population. So we reject our null hypothesis, but do so incorrectly. And depending on our alpha level, we sort of accept the fact that that may happen approximately whatever percentage of the time we choose. Now, we really haven't talked about how to control type 2 error. And remember, that's when we fail to reject the null hypothesis, but we should have. So again, sort of the opposite of type 1 error. The reason we haven't talked about controlling type 2 error is that doing so is much more complex than type 1, where we just say what it is. So type 2 error really involves several moving parts. So we're going to have to look at those. We're going to use some actually distribution curves to actually illustrate what's going on with type 2 error. And of course, we will talk about how to control it using N, which of course is our sample size. So this topic is a bit more advanced than what we've been doing, but it all comes together. You'll see how type 1 and type 2 and sample size all come together to allow us to make certain statements about our hypothesis. So all that being said, let's go ahead and dive right in. Now, my first point here, and I've said it before, I'm going to go on my little soapbox, and that is the importance of standard error. The importance of understanding standard error cannot be underestimated. The standard error of the mean, which remember is the same thing as the standard deviation of the sampling distribution, is foundational to almost everything we do in inferential statistics. So confidence intervals, hypothesis tests, and everything like that. So remember, when we're talking about our confidence intervals, we have this margin of error component here on the right-hand side, there in the red. And remember, it's sigma, which is the population standard deviation, divided by the square root of the sample size. So that is the standard error component of the confidence interval. Of course, when we're finding our z values, it plays a part there as well. So here our standard error is in the denominator. So we have sigma divided by the square root of n in the denominator. So by looking at the standard error component in these formulas, what happens to the overall size of the standard error as sample size increases, assuming the same sigma? What happens to the size of it if the sample size increases? Well, the standard error decreases. So when n becomes large, it changes that fraction. So sigma stays constant, but n becomes larger and larger and larger. Therefore, the value of that component will decrease. Now, if we're looking at a distribution, what we're saying, like physically in the distribution, it narrows the sampling distribution. Because remember, the standard error of the mean is just the standard deviation of the sampling distribution. So if the standard error decreases, we're actually going to narrow that sampling distribution. Now, when we're looking to differentiate or compare two distributions, so here, two population distributions, there are two primary characteristics we can analyze. We can analyze sort of the difference between their means. So where one mean is in relation to the other. We can also look at their variances. So how wide one distribution is relative to the other. So is the variance large and therefore the distribution's wide, or is the variance small and the distribution therefore narrower? So again, depending on the location of the means, they can be overlapping almost, or they can be quite far away. So when we're looking at the difference between two distributions, one of the characteristics will be where their means are in relation to each other. And of course, where the areas overlap or do not overlap. We can also talk about variance. So in this case, smaller variance. Now notice in this animation that the means of these distributions do not move. So the variances decrease, but the means do not move. So we can differentiate these population distributions strictly on variance. Now, of course, we can differentiate them and compare them based on both characteristics, the mean locations relative to each other and the variances relative to each other. So it's not either or. In actually most cases, we'll be looking at a combination of the means and the variances. So setting type 1 and type 2 error. Now, it is possible to establish ahead of time the acceptable amount of type 2 error in the same fashion the type 1 error is established. So if we say a type 1 error of, say, 0.05, we could set a type 2 error of 0.05 or 0.10, whatever we would choose, in the same way we would choose type 1 error. To achieve this, however, we must locate the two distributions in the proper location or alignment. So they're going to have to align in a certain way, and we'll talk about that as we go. Now, since the population means and variances are given in the problem, we will be forced to kind of manipulate, and I use that word in quotes, manipulate the sample size to achieve a certain standard error. So by manipulating the sample size, we can get a certain standard error that will sort of force everything to align where we need it to. So we will find the appropriate sample size to shape the variance in a manner that brings the distributions into alignment at the proper type 1 and type 2 error locations. And again, you will see how all this works coming up. So we have two distributions and the standard error component in the middle. So by manipulating or changing the sample size, the denominator of the standard error component, we are changing the values literally at the standard error marks. So at each of the standard error marks in these sampling distributions. A larger sample size given the same sigma will decrease the standard error, making the interval between the marks smaller. So just for example, let's say if the mean of this sort of pink distribution was 100, and one standard error was 110, that was the value, if we increase the sample size, the standard error might now be 107. So we might go from a standard error of 10 to a standard error of 7, just by increasing the sample size in the denominator of this standard error component. And again, this is fundamental to understanding how we can control type 2 error using sample size. Let's go ahead and use the same problem we've been using in previous ones, and we'll adapt it again for this topic. So Starbucks is interested in assessing customer satisfaction in the Canadian city of Toronto, Ontario. To conduct the study, Starbucks asked 25 customers in the city, compared to other coffee houses in Toronto, would you say that customer service at Starbucks is much better than average, a score of 5, better than average, a score of 4, average, a score of 3, worse than average, a score of 2, or much worse than average, a score of 1. And again, in research, we call this a Likert scale. Now, we found that the mean rating was 3.50. Also, based on this sample, and let's say other samples from other studies, we found that the population standard deviation was 1.5. So our sigma is 1.5. Now remember, the first thing we do is establish our hypothesis. So our null hypothesis is that the mean customer rating is 3 or less. Therefore, the alternative hypothesis is that the average customer rating is greater than 3. Step 2, determine the appropriate statistical test and sampling distribution. So this will be a one-tailed test. We can tell that based on our hypotheses up above. Now, Starbucks is also interested in a better than average rating. So that also tells us the direction of our statistical test. Now, since sigma is known, we will use this z distribution to do our analysis. So there is how we find our z-score over there on the right. So step 3, specify the type 1 error rate. So for this study, we're going to use an alpha of 0.01. So I'm comfortable with making a type 1 error 1% of the time. So 1% of the time, I may get a sample mean that is beyond my critical value, even though it belongs in the appropriate population distribution. We'll just assume that's what I'm comfortable with. Now for step 4, we state our decision rule. So based on our normal distribution at the alpha of 0.01, if our z value is above 2.33, we're going to reject our null hypothesis. So if we look at our sampling distribution over here on the right, we can tell from our z table with an alpha of 0.01, the area above the curve to the right, that's 1%, has a boundary or a critical value at a z of 2.33. Then we'll gather our data. So we had a sample size of 25 and a sample mean of 3.5. Now, one thing we have to know to do these type 2 error problems is what is the mean customer satisfaction value that falls on that critical value of 2.33. So we want to know sort of what mean will be the difference between failing to reject our null hypothesis or rejecting it. So we're just finding the mean on the critical value. So remember this formula we used before where we actually found the z value. Now we're going to actually flip it around. Instead of z being the unknown, now x bar will be the unknown. So our z is 2.33. That's the z at our critical value. And the x bar is our unknown. So we're going to find the mean that falls on top of it. So algebraically, we go ahead and solve this equation. And we have a critical mean of 3.699. So therefore, any sample size of 25 with a mean that's above 3.699 would lead to a rejection of the null hypothesis. Again, assuming the same sigma and alpha. So the z critical of 2.33 and the critical mean of 3.699 are two ways of saying the exact same thing. They are two ways of locating the exact same spot on our sampling distribution. So based on our alpha of 0.01, we know that 1% of our area is in the upper tail past our z critical value. Again, therefore, any sample with a mean above 3.699 would lead to the rejection of the null hypothesis. So if we had a mean of 3.72 or 3.8, then we would reject the null hypothesis because it would be in the brown area above our critical mean. Remember, we find that out by adding how many standard errors above the mean is this location. So mu sub 0 plus z of a. So again, in this case, our z of a is 2.33. And that's multiplied by our standard error. So of course, our mu sub 0, the mean of this distribution is 3. You can see that down there in the middle. Z of a is 2.33. We know where that is. Our sigma is 1.5. That came from the problem. And our sample size is 25. That came from the problem. So we found this 3.669 using this very same formula. And I put this formula on here because it's going to be very important here in a few minutes. So what about controlling type 2 errors? Now remember, to calculate the probability of type 2 error, we have to select an alternative population mean that satisfies the alternative hypothesis. There is no one type 2 error. It's different for every value of the alternative population mean that satisfies the alternative hypothesis. So remember, our null hypothesis was that the mean customer rating was 3 or less. And the alternative hypothesis was that it was greater than 3. So we could select any alternative population mean that meets that alternative hypothesis. So it could be 3.5, it could be 4.1, 3.75, 4.75. Any alternative population mean that meets the criteria of the alternative hypothesis. Now for this example, we'll just choose an alternative population mean of 4. And let's stipulate a type 2 error rate of 5%, or a beta of 0.05. So we've done a few things here. We have selected an alternative population mean that meets our alternative hypothesis, which we have to do these type of problems, and we have stipulated a type 2 error rate in the same way we have stipulated our type 1 error rate. So we have an alpha of 0.01, and now we have a beta, or type 2 error rate, of 0.05. So what region is beta of 0.05 of our alternative population mean? So if we have our curve here, we know that our alternative population mean is 4, and therefore we have to find the critical value that lines up with a beta of 0.05. So remember the way these curves were set up in our previous example, that because this population mean is above our hypothesized one, the beta values will be in the left-hand tail. So using our normal curve, we know that the 5% of this distribution has a z-value of negative 1.645. So again, we can find that in our z-table. So that is the location of the 5% type 2 error rate. Now here's the thing. These two equations for the critical value point to the same place, which we'll call C, just from different sides. So we will set them equal to each other. So look how this works. So we have our hypothesized population mean here at the bottom. So we have an alpha of 0.01. We know that's a z-value or critical value of 2.33. And our non-rejection region is 99% or 0.99 there in the middle. So now we have to align that z-value with the critical value in the beta area of our other distribution. So it lines up right there. So you can see that we have our hypothesized population mean at the bottom, our alternative population distribution here at the top, and we have aligned those two z-values in both curves. Now the thing is, these point to the same place. So we've aligned this along an axis we call C for like a critical mean, which you'll see here in a minute. So this value is mu sub A minus the Z, in this case, for this distribution, is negative 1.645 times the same standard error. That would locate that point there. Now in the bottom distribution, it's very similar. So mu sub 0, but this in this case plus, because it's to the right of the mean, Z sub A, again, times the standard error. So these two equations point to the exact same spot in the alignment of these two distributions. So what we can actually do is set them equal to each other. So here is everything carried over from our previous slide. Again, on the bottom, we have the Z critical of 2.33. That's the critical value for an alpha of 0.01. And then on top, we have a beta or type 2 error rate of 0.05. And that lines up with a Z value of negative 1.645. And again, those come from our Z distribution table. Now remember, those have to line up on the same value. But first, we're going to find the actual mean value that corresponds to each critical value in each distribution. So to find the top one, we use the same formula we used in our confidence interval video. So to find this value, we're going to go ahead and take 4, which is our alternative population mean. We're going to add it, but we're actually subtracting minus 1.645 because we're going to the left. So that's the number of standard errors below that mean we are, times the size of our standard error. So again, the 1.645 is how many standard errors below the mean we are, and then the 1.5 divided by the square root of 25 is the actual size of the standard error itself. So here we are 1.645 standard errors of this size below the mean. Now we find this out, and that is a critical mean of 3.501. Now we'll do the same thing for the bottom. Now with this one, we come up with an X bar critical of 3.699. Problem: they're not the same. So we've aligned these at their critical values, but they are at different means. So by aligning them on the same critical values, we've aligned them on different means, which cannot happen, of course. So we have a problem that we have to solve. Now remember, to get these to the same thing, what we want to find is a sample size n that will make this C value equal. So again, we've aligned these on this C axis, the C value. We want to find the right sample mean that will make these equal. So how are we going to do that? Now these two equations with the critical value C point to the same place, again, just from different sides. Therefore, we can set the equations equal to each other and then solve for n. So here's our equation for the top. So again, mu sub A minus Z sub beta times the standard error. Again, that's a lot of variables, but it's just what we just did. So don't freak out about all the mu sub A's and Z sub betas and stuff. It's just the value at C in the upper distribution. Same thing for the lower distribution. So mu sub 0 plus Z sub A times the standard error. Again, these are just pointing to the same location where these align. Now what we're going to do is, since they're pointing to the same location, is set them equal to each other and then solve for n. Just like that. So because they point to the same place, we'll set them equal to each other. Now what will happen is that n will give us a sample size which will generate a standard error that will properly align these distributions. It's almost like magic, but really it's just algebra. So we'll set them equal to each other. We'll solve for an n that will develop a sample size which produces the proper standard error to make everything line up. So solving for n to control our beta. So here's the equation we left off with, and again we're going to do some basic algebra to arrange everything to solve for n. So here we subtract mu sub a from both sides. Then we'll go ahead and rearrange everything with our negative signs. We'll combine our terms, so z of a plus z sub b times sigma divided by the square root of n. That's just simplification using algebra. Finally, we'll move our square root of n to the left and our mu sub 0 minus mu sub a to the right. So again, just using algebra. Now, of course, we want the radical sign to go away, so we'll square everything. So now we have z sub a plus z sub beta all squared, sigma squared, and then our term at the bottom, mu sub 0 minus mu sub a, all squared. And again, this is just basic algebraic manipulation to solve for n. If you need to pause the video here to take a look at this, feel free. But all we did was solve for n. So this was our final result, our final equation. So what is everything? So z sub a is the z value given the area of alpha in the upper tail of the standard z distribution. So remember, in our previous curves, that was 2.33. That was the area in the upper tail of the standard z distribution. Now z sub beta is the z value giving the area of beta in the upper tail of the standard z distribution. And again, this is sort of one of the quirks of this formula, is that even though the beta was in the lower tail of our distribution graphic, in our formula, we treat the beta as it's in the upper tail. And again, that's just to keep everything, our signs and everything correct. Now, sigma is the population standard deviation, so we get that in the problem. Mu sub 0 is the value of the population mean in the null hypothesis. Again, that's in our problem. We get mu sub alpha, which is the value of the population mean used or chosen for the type 2 error. So we have all 5 of these in our problem, either based on what's given in the problem or what we find in terms of the z values from our type 1 error we select and our type 2 error we select. Now note, if the hypothesis is a two-tailed test, we'll substitute z sub alpha over 2 where we have z sub alpha. Because remember, in a two-tailed test, we have probability in both tails. So we would just divide that area by 2. So what about this problem? So we'll go ahead and put our knowns here. So we have a z sub alpha of 2.33. Again, we saw that many slides ago. Our z sub beta, which is 1.645. And again, we're treating it as if it's in the upper tail, just for the use of this formula. Our sigma is 1.5. Our hypothesized population mean is 3. And our alternative population mean is 4. So that's everything we need to substitute back into this formula. So we go ahead and do that, and what do we come up with? We come up with a sample size, remember we're solving for n, a sample size of 35.6, which we round up to 36. So what are we saying here? Therefore, to control the type 2 error at 5%, a sample size of at least 36 must be taken. This sample size n will produce the correct standard error to align the distributions at that common C. Remember that from our previous slide? We had that sort of vertical axis where everything lined up. But the question is, what's the value at C? So finding the common C. So again, here was our equality formula we had. So we can go ahead and set these actually equal to each other. So again, we're just substituting what we know back into each one of these. Now notice we're putting in the new sample size into the denominator because we're going to find the value at this new C. So I went ahead and put in the 35.55 just so I don't have any rounding or to minimize rounding errors. We could have used 36 and just realized that any offness is just due to rounding. So substitute everything in. And what do we come up with? 3.59. So by using the new sample size, both of these formulas on both sides come up with an X critical or a X bar critical of 3.59. So that is the C value where our curves will align. And of course, we're happy about that. So let's go ahead and wrap this up. So you can see over here on the right, we have everything that we've been using up to now. We have our bottom, our hypothesized population mean of 3 down there at the bottom. We have our alternative population mean of 4 there at the top. We have the same critical values we've been using, so an alpha of 0.01 has a z critical of 2.33 at the bottom. On the top, our beta of 0.05 has a z value of negative 1.645. Now remember, the whole point was to try to find the X bar critical, or the sample mean that aligns these two. And we found it out to be 3.59. So down here in the bottom, this value is 3.59, and on top, it's 3.59. So if we have a sample mean that falls where A is, what would happen? Well, we would fail to reject the null hypothesis. That would be correct. If we have a sample mean at B, what would we conclude? We would reject the null hypothesis, but do so incorrectly. Again, that's our type 1 error. So we rejected the sample mean at B, even though it is part of this blue distribution at the bottom. Now, if we got a sample mean at D, what would we conclude? Well, we would reject the null hypothesis. It's way outside the blue area there at the bottom, and we would do so correctly. Now, what about at C? Here we would fail to reject the null hypothesis because, again, the type 2 error is where it overlaps with the non-rejection region below. So we would fail to reject the null hypothesis incorrectly, and of course that is our type 2 error. But what's going on here? Notice the means did not move. The hypothesized population mean is still 3. The alternative population mean is still 4, so those didn't move. What happened is that the distributions narrowed due to a larger sample size, decreasing the standard error. So these distributions, what actually happened is we can't see it on this slide visually, but the values along the standard error marks got smaller. And what we did is we found the exact sweet spot where the standard errors allowed everything to line up using that simple algebraic manipulation in the previous slide. And that's it. All we're doing is manipulating or changing the sample size so the standard errors of these sampling distributions line up the critical values in the lower and upper population distributions. So a quick review of controlling beta, and then we are done. So remember, controlling alpha, or the type 1 error, is easy. We just choose it. So 0.05, 0.01, 0.10, whatever. Controlling beta, however, the type 2 error, is a bit more complicated. Remember, the goal is to align the alpha and the beta regions in the hypothesized population mean and the alternative population mean, so their distributions. Now, since the means, sigma, and the critical values are set within the problem, we can then manipulate the sample size to generate a standard error that brings the alpha and the beta regions into alignment at that vertical point C. Now, this new sample size N will create a new mean critical value for our decision rule. Now, since type 2 error is controlled, we can use the phrases reject the null hypothesis or, finally, accept the null hypothesis. So before, we could not say, oh, I accept the null hypothesis. We could not do that because we were not controlling for type 2 error. But in this case, we are controlling for type 2 error. So we can use the phrases reject the null hypothesis or accept the null hypothesis. Now, we would have to redo our study with a sample size of at least 36 to control this type 2 error at 5%. And of course, to use those two phrases in the previous bullet point. So we would actually have to go ahead and redo our study, use a sample size of at least 36 in order to control that type 2 error at 5%. Now, if something changed, if we chose a different type 1 or type 2 error rate, if we had different alternative population mean we selected, that would change everything. So we're sort of assuming everything else stays the same. So we would have to redo this study with at least 36 to control the type 2 error at 5%. Okay, so that wraps up our video on how to control our type 2 error rate using our sample size. Now again, this is one of the more advanced topics in hypothesis testing, and to be honest, a lot of intro stats courses just skip right over it. But I think it's valuable because it really helps you understand what's going on in the underlying distributions, and especially when we get into the next topic, which is comparing the means of two completely different independent populations. You'll sort of see what's happening with the distributions as they align or do not align, or the variances are different, or what have you. So if you really understand this concept, when we get into the next topic, you'll have a very good foundation for grasping it very quickly. Okay, so just a few reminders. If you're watching this video because you're struggling in a class, stay positive and keep your head up. If you're watching this, it means you've accomplished quite a bit already. You're very smart and talented, and you may have just hit a temporary rough patch. Now, I know with the right amount of hard work, practice, and patience, you can get through it. I have faith in you. Many other people around you have faith in you, so should you. Number 2, please feel free to follow me here on YouTube, on Twitter, on Google+, or on LinkedIn. That way, when I upload a new video, you know about it, and it's always nice to connect with my viewers online. Number 3, if you liked the video, please give it a thumbs up, share it with classmates or colleagues, or put it on a playlist. That does encourage me to keep making them for you. On the flip side, if you think there is something I can do better, please leave a constructive comment below the video, and I will try to take those ideas into account when I make new ones for you. And finally, just keep in mind the fact that you're on here trying to learn, trying to improve yourself as a student or as a business person. That is what really matters. I firmly believe that if you have the commitment to learning, that the results will take care of themselves. So, thank you very much for watching. I look forward to seeing you again next time.